So in this video, we are talking about cyclic quadrilaterals. Now, we talked about what this was right at the start of this series. So if you're not too sure, you can have a look back at that one. But it's basically just quadrilaterals where the vertices lie on the circumference of a circle. Hence why it's a cyclic quadrilateral. Now, the first theorem that we're trying to prove is that the opposite angles of a cyclic quadrilateral are supplementary. Now, we're told here that O is the center of the circle, ABCD is a cyclic quadrilateral, and we want to prove that angle DAB plus DCB equals to 180 degrees. So we're looking at DAB and DCB. We want to prove that these add to 180 degrees, and the same thing for ADC and ABC. So we have, as you can see from here, I've joined OD and OB together, so with these dotted lines. Now, we know from a circle theorem that angle DAB equals to half of DOB. So it's half of this angle here. And the reason why, if we remember our previous circle theorems, the angle at the circumference is half the angle at the center. Okay. We also know that angle DCB is half of the angle, half of the reflex angle DOB for that same reason. So I'm just going to put these little quotation marks just to say it's the same reason. Now, we know that if I were to add these two angles, angle DAB and DCB, it would equal to half of DOB plus half of the reflex of angle DOB. But we know that if we factor out this half, if we have the angle DOB and the reflex angle of DOB, those two are angles at a point. So they add up to 360 degrees. You can see the revolution there. So DAB plus DCB equals half multiplied by 360 degrees, because those two add up to 360. And that gives you 180 degrees. So we have proven this part here. And we can say similarly, if we did the same thing, let's just rub this part out, but we drew it in like this. We would notice the exact same thing happening. So our angle of ABC would be equal to half of this angle at the center, and this angle ADC would equal to half of the reflex angle here at the center. So for the exact same reason, we can prove that ADC plus ABC equals to 180 degrees. So what I'm going to write here, we can just write similarly by joining CO and AO, it can be proven that angle ADC plus angle ABC equals to 180 degrees. Okay, so with that in mind, we're going to try to find the value of the unknown here. So we know that angle X plus 87 will equal 180 degrees. We know that because opposite angles of cyclic quadrilateral, I'll say ABCD, are supplementary. Therefore, X equals to 93 degrees. Okay, So moving on to another one. We're trying to prove that the exterior angle of a cyclic quadrilateral equals the opposite interior angle. So we're trying to prove here that ECB equals to DAB over here. Okay, so to start this off, I'm going to let angle ECB equal to X, just call it X. So therefore, we're going to say BCD, angle BCD, is going to be 180 minus X. So because this is the angles on a straight line. Okay. Now, we can say that angle DAB, this angle that I've labeled at the top, equals to 180 minus angle DCB. The reason is what we discovered in the last circle theorem. So opposite angles in a cyclic quadrilateral A, B, C, D are supplementary. Okay, so therefore we can say that DAB equals to 180 minus 180 minus X. Now, if we expand these brackets, we have 180 minus 180 plus X, because we have a double negative here, which just leaves us to a size of X. So with that in mind, we can therefore say, because DAB is the same size, X, as ECB, therefore we can say that ECB equals to angle DAB as required. Okay, so last part here, we are just trying to apply this theorem here. So we want to find the size of ADE, this exterior angle here, and we can say using our circle theorem that angle ADE equals to degrees. The reason being that the exterior angle of cyclic quadrilateral ABCD equals the opposite angle, interior angle. Okay, so these are the two sort of primary theorems with the cyclic quadrilaterals. There are a couple more which we will talk about in the next video. But thank you so much for watching, and I'll see you there.